I would like to tell you why we need deep generative modeling. And if you think that I will show a lot of beautiful images, so it's not this talk, I will try to convince you that there is something else that we need to achieve AI. And one of these components that we need is, in my opinion, continual learning that we had a great lecture on Friday. And the other component is generative modeling. We have quite, I would say, plenty of time. So if you have any questions during the talk, so just please interrupt me, okay? It will be better, I think. All right, so let's start. And let's start with a very simple example, all right? And let's first answer the question whether generative modeling is important in the first place. And let's say that we have a standard task. We have a neural network that tries to classify images. And let's say that we have such a network, it's trained, we have some image of a panda, and let's say that our neural network is perfectly trained, we have really high probability of this class. Now, if we add a little bit of noise, then for us, human beings, we still see that this image is exactly the same. There is no change. But for machine, for neural network, it could be something completely different, right? It could be that actually now the probability of panda, it's really low, and probability of some other category, it's really high, right? And this is, of course, the whole field of adversarial examples and so on. But in my opinion, the reason is also different, that we should also look at something else. We should look into some kind of understanding, some kind of, it is too fast for me. So we should look into some kind of semantic understanding, in this case. In general, some kind of understanding what's going on, all right? So let us consider, this simple example shows us that, first of all, discriminative model is probably not enough to have a proper understanding of reality. This is always something like, for some given input, give me some value of, probability of something else, some prediction. We need some kind of notion of uncertainty. So having just neural network with softmax is also not enough, all right, to give proper uncertainty. And ideally, we should understand what's going on in our world, okay? And by understanding, I don't mean interpretable model, that we can look into the model and say, okay, this means, one quantity and this means something other. I'm thinking about that, all right, when I see a pillar, I know this is a pillar. When I see a human being, I know this is a human being. If I see a Martian from other planet, I don't know maybe what is that. This kind of understanding. So what I know that if I learned on some data, I know that these are data that I was trained on, not something totally new. And this talk is about a possible solution that generative modeling is the way to go. And the next slide, maybe I will stand here. All right. So now we have a different example. Let's say that we have two categories. We have horses and cats. And we can train a model, discriminative model again. So we have conditional probability. Let's say that we have really well-trained model. We have a decision boundary, and it's fine. Or we can have a joint model that is factorized in the following way, that it's probability, conditional probability, and probability of x's. So in this case, objects, cats and dogs, right? Or images in general. And let's say that we have, again, a trained model. So what is the difference between these two models? So if we have a new data, something that we have never seen in our training data, if we apply this discriminative model, we can have, for instance, probability this lies on this side of decision boundary. It could give us high probability of a horse. So in other words, decision is highly probable, okay? Which is obviously wrong, because this is never something that we've seen so far. But if we apply generative model, so in this joint probability, So we can have high probability of a horse, but very low probability of the object itself, all right? So now in the end, we can have an uncertain decision, all right? So to give you another example, for instance, let's say that we have a robot that is walking in some environment, and then there is something like some obstacle that is totally new to this robot. So I would expect that this robot will send me a signal that, hey, Mr. Human, there is something that I've never seen so far, I don't know what to do, all right? Instead of saying that, all right, this is a dog, so I can go through that or something like that. Right. So what is important in my opinion, and this is what we'll focus today, is to learn this quantity. That is in general pretty difficult to train, but we have, fortunately, we have some tools so far. And where we can use this generative modeling paradigm, let's say, we can use it in many, many applications. So first of all, we can use it for image analysis. This is all these papers that you read, they always show some nicely looking images. We can use it to graph analysis, for instance, for drug discovery, audio analysis, reinforcement learning, medical data, and so far, NLP, and so on. We can use it everywhere. And how we can, let's say, create some kind of taxonomy of generative models. So there are, I would say, three main groups. First one is explicit model that we just, factorize joint probability of, for instance, pixels, and we have autoregressive models like pixel CNN. We can use the change of variables formula, and then we have these flow-based models with real MVP, GLOW, and so on. Or we can have latent variable models, like, for instance, VAES that we'll talk about today, and GANs that we'll skip totally, because implicit models, they cannot give us probability for given object, right? So that's why it doesn't fit to this talk. I'm not a big fan of GANs as well, so it's maybe another reason why I skip it. All right. So, all right. So here we have another explanation of this model. So if we look at different let's say, objectives or properties of this, if we look at training, if we can calculate likelihood function or not, if we can sample easily or not, or we can use for compression, so then we will see that actually different models are useful for different tasks. And for instance, autoregressive models are very stable in training. They can give us exact likelihood, but for instance, they are pretty slow for sampling, and they cannot be used for compression because we don't have any kind of data, some low-dimensional representation. Flow-based models are very similar, however, maybe they are faster in terms of sampling, but still no compression. If we look at implicit models, we know that we can generate beautiful images, for instance, but then my question is, all right, why do we need beautiful images in the first place? Maybe for some apps that we want to change our face to some older person. But in decision making, it's a little bit, yeah, I will not go into that maybe. And then we have prescribed models like VAEs. And then they are really cool because training is stable, sampling is fast, compression, we can use it, but of course, likelihood function, we need some kind of approximation, right, of that. And today I will talk about flow-based models and VAEs, but in the opposite order. First VAEs maybe. And another perspective, it's always good to have some kind of simple pictures in mind, and to have this very high level of abstraction, how these generative models work. So let's think about spherical cows. So do you know this joke about a physicist and mathematician modeling? There are some physicists in the room. Yeah. So the joke is not so funny, so I will not tell it. But the general idea is that the task is that what if we want to model cows, and then we can look at it from one perspective, and this one perspective is keeping original dimensionality, but then we can say that actually, can we somehow still simplify the object? And in this case, yeah, it's working. So in this case, we can treat it as a spherical cow, right? But still, this is the 3D object. Or we can look at it as we can actually still have a circular cow, but now in 2D. And this is the latent variable model, okay? So we in some sense compress it and try to keep everything that is important still. And so please keep in mind this slide, okay? And this is everything we need to know. And now something about some details. And first we will look into, all right. First we will look into deep latent variable models, okay? Because this is a little bit simpler from generative perspective to think about modeling. All right. So in general, of course, modeling in high-dimensional spaces is really hard. So when we have thousands of pixels, it's really hard. But also why it is hard, we can see here, we have a beautiful horse and very handsome person. and if I ask you, do you see a difference between these two images? Black spot. Precisely. We have this black spot here. But if we don't care about this black spot, we still see this handsome guy, right? It doesn't destroy the whole image. And that's why this is also so difficult, because one single image, one single pixel is basically nothing. It contains no information. But if we look at patterns, couple of pixels, so then we see something there. So you see that there is, if we want to model all possible, let's say, of course it's impossible, but if we are able to model all possible dependencies, this would be crazy model. We would never fit anything to data, right? This would be just super problematic to, first of all, propose all possible dependencies, and second of all, to train such model. And possible solution to that is to think about it in this latent variable model way. So what does it mean? It means that we assume that there is some low-dimensional, we can say, representation, a code of our reality, or if we want to be more mathematical, you know, sexy, we can say that there is some low-dimensional manifold, like here in this 3D. It's this 2D manifold in 3D space, and we can, yeah, please don't look. This is just to have some kind of probability there. It's not super maybe correct, but just to see that we have some probability on this manifold. And now we have a beautiful generative process. So first, we can say that we need to sample this low-dimensional information, this code, and then having that, we have some kind of decoder or generator that will give us this high-dimensional object, all right? So if you properly understand generative process, actually all models you see in literature, it's always about it. If your generative process is correct, you don't cheat by adding some information somewhere. If this is correct, you have always a nice model and nice paper, eventually, hopefully. And so the idea is the following, that of course, now we can to make an example of horses. So we can sample from this manifold. We go through decoder, stochastic decoder, or deterministic one. It's also fine. We can generate these high-dimensional objects. It is, of course, beautiful, but it has a huge problem, namely the marginal likelihood function. So if we take this log marginal likelihood function, we have this log, and then we need to marginalize over all possible latent codes, right? In any case, if this is even discrete, it will be exponentially many possible z's. In continuous case, we have even worse case, but still, this is to calculate this integral. It's impossible, and using simply some Monte Carlo sampling or whatever, it's still inefficient, at least for training, right? If we have thousands of pixels, for instance. So this is problematic. So how we can train it efficiently? One possible approach is to use variational inference. What does it mean? We can look at it from this very simple perspective. This slide is taken from, I remember I learned it from Zubin Garamani. He explained it in this one slide, and then I had something like, wow, this is actually simple. And it makes a lot of sense. So what do we do? So we take our log marginal likelihood, then we introduce, so we multiply by 1, right? So we introduce something which is called variational posterior. Then we use my favorite Jensen's inequality. So we go with log into the integral and we got lower bound. And then if we play a little bit, so we just, apply log to this and so on, we can get reconstruction error and we can get regularization, right? So if we think about it again, so if we forget this, so this is something like going from X to Z, so from high-dimensional space to low-dimensional space, and then from low-dimensional to high-dimensional space again. And this is something like how I, in some sense, regularize this latent space so that this variational posterior, it's somehow close to the marginal over Z's. And now if we go a step further, and we say that this is our decoder, this is our encoder, we actually end up, and this is, I don't like name prior because this is not a real prior, it is marginal over Z's. So we end up with variational autoencoder, right? So easy, we know from yesterday, if you want to use Pyro, you can implement it in, I know, using 20 lines or something like that. And you can apply it in many cool cases. And so if we look further into that, of course, this is just math. This is our objective function right now. So instead of looking into this troublesome quantity with log of integral, we can actually get something that is well-behaved, and because we want to maximize log marginal likelihood, so we try to close the gap between this lower bound and original objective. And in general, how we parameterize these distributions. So here is where deep learning comes into the game. That's why it's called deep generative modeling. We can actually parameterize this variational posterior using a neural network that will give us as an output parameters of a distribution that we assume, for instance, Gaussian. And then the decoder, it's again, or the likelihood function is again parameterized by some neural network, okay? And another cool thing to lower variance of all estimates, all this also these expected values, we can use reparameterization trick that says that if it's possible, you should do it. So just move the stochasticity to some independent random variables, okay? So in the case of Gaussians, it means that we just have standard Gaussian random variable, and then from the standard Gaussian random variable, we can get any other Gaussian variable by just shifting it by mean, and by playing with variance, we can get more picky or less picky Gaussian, okay? And why VAEs are so nice and why I love them personally is that, first of all, we can go through a bottleneck. So since we have a bottleneck, so we ensure that, at least we hope, that we get some kind of compression of our data so that the most significant information is in the code. And we can, for instance, send this code. And then we can, of course, send it and decode it back. But also, because we have marginal over codes, so we can also generate new data points. So we can just sample and we can just decode it back, right? And so on. By the way, these images, they are real images of some cells in histopathology slides. But so what are common issues with VAEs? So first of all, weak decoders, if we take not powerful enough neural networks for decoders, we'll get bad generations, but actually maybe in most cases very bad reconstructions. If we take weak encoders, so we'll get, of course, bad latent representation. So it's again something inefficient in many applications. If we have weak marginals, so actually again we'll get bad generations, and we'll discuss it a little bit today. And also variational posteriors. So what kind of family of distributions we should use? So in the original paper from Diederik King and Max Welling, so they just assumed Gaussians because it's easy to reparameterize, and it's simple, but of course it's very limited. And in general, what people do with these three components, so if we look at the generative process, so we can pick different marginals. In the simplest case, it is just fixed standard Gaussian. But many people claim that it's better to train this marginal using different ideas, like autoregressive modes, normalizing, VAMPPRIOR, we discussed today. And if, of course, we look at the decoder, so people use, again, some ResNets, draw, autoregressive models, normalizing flows, and so on. And if we look into encoders, so we will discuss normalizing flows today, maybe discrete encoders, very briefly I will mention that, a different distribution than Gaussian, and also you can use some other fancy things like group theory and so on. Some people also claim that elbow itself, so the evidence lower bound, the lower bound that we work as our objective, it's not good enough, and we can maybe combine it with adversarial learning to get more crispy images if we want, maximum discrepancy or Wasserstein autoencoder. So today we will start with normalizing flows because first we'll discuss it in the context of VAE, but further we'll just use it as a model by itself. So what is the idea? And the question is, so if we rewrite, if we play a little bit, we can explain elbow as the log marginal likelihood minus Kullback-Leibler term between variational posterior and the real posterior, okay? And what we do, we try to minimize this distance. And of course, if this is our family of posteriors, variational posteriors, so we will pick some distribution. But if the family is more flexible, right? Of course, we can get closer to the real one. Okay, so the idea is that how to formulate more flexible family of variational posteriors, right? So if we just simply take Gaussians, so probably this is not flexible enough in many cases. And also another thing is that how to propose such family of distributions that it will be also easy, computationally efficient. And one approach that I had, even I was lucky to listen to this original presentation of that at ICML in 2015. And I remember I didn't understand a word from this presentation, but I knew that this is something cool. And I have to do it at some point. So the idea is really simple. So the idea is that we start with some so-called simple distribution. So for instance, it is just a Gaussian. And then, by using invertible transformations, if we use a sequence of invertible transformations, oh, something is wrong here, we can actually transform this distribution to something more complicated, for instance, multimodal, okay? So to also somehow visualize it, so let's say that we have some sand that is shaped as Gaussian, right? And let's say that my hands now are these invertible transformations. So we can record a video and then play it in reverse order. And now my hands are just doing something like, separating this sand. And I will get multiple modes, okay? And then if I play in reverse, these hands will go back to Gaussian, okay? And we can also think about it as another neural network that is simply transforms it to something more fancy, but with a constraint that this must be invertible. Okay? And of course, you can ask, is it enough? So the only thing that is a little bit troublesome is that we need, because this is the change of variables formula, because it must be probability, so it must sum to 1, right? So of course, if we need to also care about volume of this new random variable. So in other words, we need to scale it properly so that this part here sums to 1. But of course, now this is the determinant of Jacobian, right? So first derivatives. So of course, we can feel already that derivatives, it will be maybe difficult to calculate. Another cool thing is that if we introduce these normalizing flows, so we modify our variational posteriors, so the only difference in the original elbow is that we get a sum of this log of Jacobian determinants, okay? So basically, also, if you think about coding, so it's basically your original code for VAE with slightly modified objective. And now the main problem here is to somehow think how we can efficiently calculate this Jacobian, right? So computer scientists, programmers are lazy in the first place, right, always. And deep learning people are even worse. And so we have to think how we can help ourselves. So first thing is that we can propose something which is called volume-preserving flows. So some transformations that they don't change volume, then we'll get Jacobian that is simply 1. Okay? And if this is simply 1, log of 1 is 0, so it disappears and it's cool. We don't need to change anything at all. The problem is that volume-preserving flows are not so flexible, unfortunately. But we can also think that, all right, so if this is possible to get this volume-preserving flow, so maybe there is some other way that we can easily calculate this determinant. And so this was the first idea of Danilo Rezende and Shakir Mohammed. They called planar flows. So the idea is the following. We have something that, if you are familiar with neural nets, so this is a ResNet in some sense. So we have the original previous input and then some transformation. And this transformation in this case is one single neuron. Okay? So you see that we have something like ResNet with one single neuron and this skip connection. And it is actually, of course, not so flexible. It's one single neuron. But at least we can easily calculate the determinant of the Jacobian. So we can do that by applying matrix determinant lemma. So we know from algebra that we can do it in the very efficient way in linear cost, right? So we know analytically how to calculate this determinant of Jacobian, which is actually cool. But the problem is that we need to, because this is one single neuron, so we need to apply a lot of these transformations to get something useful. Because it's, again, if you think about my incredibly good example with this sand, so it's something like having one hand all the time and dividing it, right? So it's not so great. And of course, the question is, can we generalize it, but in such a way that it's still efficient to calculate, all right? And then this is a question that we had with my colleague who had an internship in Amsterdam, Leonard Hasenklever, and we started thinking how we can do that, and we decided that, all right, let's be smart, and just instead of one neuron, let's use more neurons. It's of course brilliant, but of course this is not so easy because we don't get anything at all. It's something like very difficult to calculate this stuff. And how to calculate Jacobian? We then realized that we can use something which is Sylvester determinant identity, so generalization of this matrix identity. And we can calculate it in this way. It's fine, but still, we need to somehow calculate it, and in general case, this is not easy, right? Because we have matrix multiplication, we have multiple of such transformations, so it will be not easy. But then, we realize that, all right, it's always good to look into algebra, what kind of stuff we have there, and maybe we can use it. And so our idea was to use QR decomposition, right? We can take these matrices here that are this, let's say, a neural network, and if we apply QR decomposition to the matrix A and B, maybe we can get something, right? QR decomposition, of course, is of a matrix that we have a triangular matrix R and orthogonal matrix Q. And if we will share orthogonal matrix between A and B, right? Because this is the part that is very difficult. So we will get that we have orthogonal matrix transpose times orthogonal matrix that gives identity matrix, okay? And then what we get a product of triangular matrices. This is diagonal matrix plus diagonal matrix. So now the cool part of it is that we can now efficiently calculate this Jacobian, still having more powerful transformation. That it's something like we can say, instead of having one neuron, we can generalize it to as many neurons as we have number of variables z. And now, another problem. Of course, this is always some problem. First problem with this laptop. It's something not working. All right. So now, of course, the problem is that when we train by SGD, stochastic gradient descent, so the question is how to keep this matrix orthogonal, right? It's again, if you think about it, maybe you had this problem in the past. It's not so easy to keep this matrix orthogonal. But then again, as a lazy deep learning person or computer scientist, we look into literature. When we dig out old paper from 70s, that there is actually an iterative orthogonalization procedure. And we can use it because if you think about it, if you look at it here, we can still backpropagate through that. So it's fine. We don't need to play with something difficult. We still can use autograd, and it will learn. And it turns out that actually it learns pretty well. And this is the interesting because we can first, as I said, we can backpropagate through that, but we can also control the bottleneck. So how many neurons we have inside, right? So of course, if we have less neurons, less calculations, it will work faster. Another idea is that we can use householder transformations. So this is standard thing to represent any orthogonal matrix. But then we cannot have any bottleneck. So it must be always the same dimensionality as the original Z. And last method, so I was sitting with Rianne Vanderberg that joined this project at some point. And she was saying that, hey, we can actually use the simplest possible orthogonal matrix, so in other words, permutation matrix, right? This is something that real MVP or inverse autoregressive flow uses. So this is something like super easy, so we just permute every second step. And then, oh, something moved, but, so we have this one single step of our Sylvester flow. We have 3 options to keep this Q orthogonal. And then we are also thinking to make this more powerful, we used hypernets, so additional neural network that was predicting parameters, this Q and R. It was actually turned out that this is very important and gives us very good results. So first, some results on the most challenging data set in machine learning, MNIST. And then we compared it to IIF, so at that point, state of the art, and planar flow. As you can see, we got better results in terms of elbow and negative log likelihood. So this was really cool. We're extremely happy. Then we applied it to other challenging data sets, Vrije faces, Omniglot, and Caltech. And again, except Vrije faces where there are really little data, so these models, they're overfitted in some sense. But on Omniglot and Caltech, we got really much better results if you compare it. So having this difference of 2-3 knots, it's actually quite a lot. And so the takeaway message from here is that actually we can get a better model and better latent representation. All right. Any questions so far? Yes?
Did you use the same orthogonal matrix to represent A and B matrices?
Yes, this is shared orthogonal matrix.
Okay.
Right. Then I had the pleasure to collaborate with students at University of Amsterdam, and we are working on something different. So here a little bit of backstory of that. So in this paper, a group from Denmark, from Copenhagen, they were asking very, very interesting question. Is that so? This question is here, but in words, it's something like, will geodesics follow data manifold? What does it mean? That if we have data and they are in, mapped to 2D, the question is that if we calculate geodesics, so if they will follow data manifold. It turns out that after training VAE, the answer is no. So what does it mean? It means that if I want to go from this point to this point, the path that the interpolation between them will not go where the data points lie, but it will go just through the center, which is of course very bad because it goes through a region that is of low probability, right? So now if you see some papers that they show this linear interpolation between 2 points in latent space, and if you see some very weird artifacts in these generated images in the middle, it's probably the reason for that is that it goes through some low probability region in this latent space. And so in this paper, they said that, all right, let's try to model this uncertainty better. They had some RBF kernels and so on. But actually, we started thinking that, all right, if we cannot force our model to go follow this data manifold, so maybe we should use different model. So if for instance, data is licensed in circle, so maybe we should use a proper data or distribution for latent space. And then we started looking to Gaussians. It's always good to have this, weak distribution to find against, and actually Gaussian is pretty weak. So, and why? Is first of all that Gaussian is concentrated around the origin, right? So there is always possible bias. And the other thing, and I see that so this is cluttered, but the idea is that if we have, for instance, here original data lies on a circle, and if we train Gaussian VAE, because of the prior that is standard Gaussian, we try to pull all these points to the origin, and then if we want to calculate, also this point that is cluttered here is that if we want to calculate distance between this point and here, so using Euclidean distance is of course false, because it doesn't take into account going on this geodesics. So what we decided to do, and another thing is that in high-dimensional spaces, Gaussian distribution actually puts probability mass on a shell, something like if you go to high dimensions, it's like lying on a hypersphere. So we took these facts together, and we decided that, hey, we can maybe use a different distribution, and if in high dimensions Gaussian still concentrates on a hypersphere, so maybe we should use a proper distribution. In this case, von Mises-Fischer distribution, that it's still exponential family of distributions. and it puts mass on a hypersphere. And really, my brilliant colleagues, students, Tim Davidson, Luca Falorzi, Nicola De Cao, so they did all this, you know, dirty stuff, implementing and using different libraries to make it happen. And we discussed that actually if we take a uniform distribution on a hypersphere, it is possible, right? But for instance, in Rn space, we cannot put a uniform distribution. But in this hypersphere case, we can do, and we can calculate Kullback-Leibler, which is von Mises-Fisher and uniform over hypersphere. Then we can also easily sample from von Mises-Fisher. It's, again, some old work. And we can also apply reparametrization trick using rejection sampling, okay? So they did everything together, they put it together, and we got very interesting results. So first of all, again, MNIST. So if we train a two-dimensional latent space, so this is what you in general get in VAE case, and this is what we got, right? So now you see that this is all latent points lie on hypersphere, right? And what is interesting is that it really clustered these points really nicely, okay? And when we started looking at negative log likelihood and reconstruction error and Kullback-Leibler term, we are really happy because up to dimensionality of latent space 10, we're really better than Gaussian case. When the dimensionality got higher, we got worse results, slightly worse results. But in terms of reconstruction error, we are always better and significantly better. The problem here, just looking at log likelihood, is a little bit misleading because Kullback-Leibler, we have this von Mises-Fisher against uniform, right? So the more dimensions we take, the difference is getting larger and larger because it's not so easy to fit uniform distribution anymore. Here is the latent, this is the semi-supervised case. Here you can see that it's again this spherical latent space. Again, some very good scores. And eventually also in Amsterdam there is Thomas Kiep who works with convolutional neural networks, graph convolutional neural networks. And we applied it to his graph VAE. And again, by having a different topology of the latent space of this hyperspherical, we're also able to get better scores. So this is really, really interesting paper in the sense that, you know, maybe different topologies of latent space, we can take them into account during modeling. And then I also was thinking that actually when we have this generative model, we have very weird behavior if we take this marginal distribution to be standard Gaussian. And we worked on something called VAMPPRIOR. And what is the story behind it? So if we train standard VAE, this is the standard Gaussian. We have some small Gaussians given by our encoder. So we can see that there's a lot of something that people now call holes, right? So there is this discrepancy between, let's say that these are these encoders for different given training data, and there's this big mismatch. And if you actually train a VAE, you can very often get some very weird objects, like in this Vrije faces case, something like, you know, Freddy Krueger-looking face, or some negative face, right? And everything is because, for instance, this region was never encountered by decoder. So it starts fantasizing in some sense, because it's not obvious what to do here. So ideally, we should have such prior that will cover these regions of encoder, right? That for which we got data. And then, of course, if we sample something here, it will be somehow similar to these points over there. And so this was our motivation. And I will say it again, but you will think that I'm very lazy. But we are lazy again, and we are thinking that instead of, figuring out what kind of prior we should use, using, normalizing flow and so on, we started thinking that maybe there is some optimal prior that we can derive from elbow. So we played with elbow. So this is we calculate expected value of log marginal distribution over all data points, training data, and then we play with elbow and we get, again, this reconstruction error. Here it's something new, mutual information between X and Z, and Kullback-Leibler between Q of Z, so this is not the encoder, this is something different, and our original P of Z. And now the question is, what is the optimal P of Z for which this elbow is, maximized? And what is this strange thing Q of Z? This is something which is called aggregated posterior. So we sum over all possible training data we have, and we calculate this mixture of Gaussians or mixture of posteriors. And it turns out that this component will be 0, right? So it will be best possible elbow if we'll just simply set this prior to be this aggregated posterior, right? It's not quantum physics. It's very easy because it's written here. It will be 0 only if these two distributions are the same. And we were pretty excited. I remember meeting with Max, and we were really something like started Googling if no one did it before, and something like, actually not. And so we were super excited. Then we realized that, oh wait, that we need to sum over all possible data points. So when we have, again, MNIST, and even for MNIST it's 50,000, so it's something like we cannot do that. And then it was something like, hey, but in Gaussian processes, they had exactly the same problem, right? And then they came up with this idea of sparse Gaussian processes, and they actually started using something which is called pseudo-inputs or inducing points or something like that. And yeah, I said to Max that, okay, so maybe we can also propose to use some fake data points, that there will be only k of them, so we will start approximating this enormous mixture of posteriors. And because we are deep learning people, so we'll treat them as parameters, and we will just train them by backpropagation, right? So this is the cool part, of course, is that this is definitely multimodal, so it should be able to somehow fit this aggregated posterior, approximate it. And so let's train it by SGD. Of course, Max was a little bit skeptical because, just training this, high-dimensional object with SGD, so we couldn't predict what we'll get, but what we got was actually really cool. So here you see for this data sets, you see trained pseudo-inputs. So I really did no magic. It was just simply setting this as parameters, running autograds, Adam, and whatever, and we got these results. So you see that actually in this model, these pseudo-inputs, so these fake data points, they resembled exactly real images, real objects. So in this MNIST case, they were digits. Here we got some these omniglot characters and so on. Here it's maybe less obvious. And here you need to believe me that there are some faces, or fairy faces. Then, of course, we looked into, okay, I have one pseudo input, but is it something that it will always generate me the same object, right? So it's somehow overfitting. But it turned out that not. So the content is there. It's always generated 8, but with different styles. So it was really cool. Then, of course, samples, maybe I will skip it, and reconstructions. So it turned out that because we have better fit between aggregated posterior and our prior, so our generative process was also better. And in the end, the last couple of minutes, I want to spend on flow-based models. But here I will not go too much into details because it's also not so complicated, because we had already something about flows. So now instead of using some variational stuff, we work exactly directly on the high-dimensional space, or on pixels. So now we apply this invertible neural network, so these invertible transformations, that from simple distribution we can go to something really complicated, and we can go back by definition of invertible neural networks. And now this latent space and pixel space, they have exactly the same dimensionality, okay? So no compression here. It was already presented in 2013, but in 2016 it was the main breakthrough. And again, to remember, this is the spherical cow, right? Because we have exactly the same high-dimensional object, but somehow simplified. So it's like this multimodal distribution. By using invertible neural network, we can simplify it to some unimodal. All right, and how does it work? So we need to now transform or propose such a neural network that will be invertible. And in 2016, Google people, with Sami Benja, not Joshua, I think that Joshua was somehow jealous for this paper because it's really well-cited paper right now and really cool. And so what they proposed, they actually said that, all right, we can cut in half our input to neural network. First part is untouched, and the second part is using the previous part, this untouched part, with something which is called scaling and translation. And we just modify the second half, all right? So why this is cool? Because this is invertible by design. If now I want to invert it, so I have y and I want to get x's. First part is easy. I just change places. And this one I can very easily invert. This should be not this dot, but division. So this is invertible by design. And if we now stack this this is called coupling layer. If we start stacking this coupling layers, we can get pretty powerful model. The problem is, of course, still with Jacobian, but it turns out that Jacobian is easy because it's triangular. And here we have only on diagonal, we have, because if we calculate derivative with respect to x, we'll only get this scaling. So determinant of Jacobian of triangular matrix is just product of the diagonal, and we can easily calculate it. It's really cool paper, and in 2016, with not so nowadays big neural networks, they were able to obtain very good results. So it's good also that this beamer gives a little bit blurry image, because probably you cannot see which is real and which is fake or which is generated, right? Do you know? Sorry? Yes, exactly, because you are in the first row, that's why. But if you look into some other data set now, you see this looks a little bit weird. This is better. But in general, I remember reading this paper and being very jealous because it's really cool. And then in 2018, Dirk Kingma and Darival from OpenAI, they trained real MVP with slightly changed architecture, but importantly with 1,000 convolutions. And they were able to get even better results. And these are images generated by a model. Of course, we can see that somehow the background is maybe a little bit, fake, that it's always maybe black or white. But if you look into these faces, they look amazing, right? And yeah, it's really interesting. And also this latent interpolation, so you can also see that if we interpolate in this, let's say, spherical cow, so this simplified space, so we can go from, what is his name in this Game of Thrones? Yeah, and in Game of Thrones, it's what's the name? Exactly, from Tyrion to other actor, so we can see that actually you can see that actually the skin color changes and shape and so on. It's really nice. Right. Right, and very recently, this will be a work presented at NeurIPS from my colleagues from Amsterdam, Emil Hocheboom, it's a brilliant PhD student, Jorn Peters as well. So they proposed something even better, something which is called integer discrete flow, where there is no need to calculate Jacobian. So it's even better. And then this is CIFAR10. It looks really decent and really nice. And also it is possible to do something which is called predictive coding. So you send only 50% of this original code, and you generate everything else. And you see that actually this is maybe, we see that this is a dog, but it looks really, really nice. This is the original dog, and this is dog. So you can even use it for compression. All right. All right, and something a little bit the last minutes for future directions. So first of all, of course, blurriness and sampling in VAES. So this is that people always complain about. But it also gives us very interesting future directions. So for instance, how to avoid sampling from holes. Can we follow geodesics in latent space? Maybe we can use somehow geometry in decoders. Maybe we can build also temporal decoders. So these are these questions that are very interesting and still not solved. Another very important issue from a practical perspective is that can we use VAES for compression? The answer is yes. So this year from being Qualcomm, we published a paper, and we actually applied VAES to big images, something like 200, 300 pixels on 200, 300 pixels, so not so toyish anymore. And we are able to get really good reconstruction using very little of code. So it's the trick was to use deterministic and discrete encoders because it simplifies objective. So then if this variational posterior discrete and deterministic, so entropy disappears. And then also, of course, we used some 3D convolutions, but another question is, can we do better? Can we use some kind of temporal dependencies? We also need very powerful priors, so can we use something more powerful or more flexible or more computationally efficient? We use pixel CNN, which is, of course, very slow for sampling. So these are another questions. So this field also just started, so there are a few papers on that. People in reinforcement learning, active learning, so it's also incredibly interesting, I think, to put this like in this world model paper from my favorite Jürgen Schmidhuber and David Ha. So they put VAE inside reinforcement learning loop. So can we maybe work on that? Maybe we can combine VAE with flows, or maybe put flows or something like that. So can we formulate policies in latent space? So can we have some better notion of sequential dependencies? It's really, in my opinion, very cool and sexy field. And another point, and this is something like going back to this first slide, because I was talking all the time about P of X, but what about P of Y given X, so our classifier? So now there was a paper, I forgot the reference to this paper, but paper from Erik Nalisnik and others, hybrid models with deep invertible features, I think. So they used GLOW to model P of X, and on top of this Z space, right, so this transformed space, they put a simple linear model, okay, as a classifier. So in some sense, this model here was used both as a quantifier or probabilistic model to model P of X, but also as a part of classifier. And they got really, really nice and good results because they were able to distinguish out of distribution points. When they trained on one model and they got some, let's say, likelihood of them, and when they showed data from other data set, so they got really low probability. So instead of looking at classifier just by looking at P of X, it is possible to just put here a line, and you know which data it's outside of your distribution, so something that you never train on, and what are points that you train on, right? And that's it. I think I went over time, sorry. Thank you very much.